Hello, this is Joseph Vadalero presenting the first lab of the spring 2021 semester in Physics 2211. The goal of this lab is to observe the motion of an object, in this case, a standard baseball, that is moving at the same speed and has no change in direction. With these observations, we will compare the experimental data found using Tracker with the predicted data found using the GlowScript IDE. We are attempting to prove the concept that Newton laid out in his first and second laws, otherwise known as the momentum principle. For the purposes of this lab, the most important part is that an object that is in motion stays in motion unless acted on by an outside force. There are two formulas that we need in order to correctly predict and understand the motion of the baseball. The first is the velocity update formula. Final velocity is equal to the initial velocity added to the quotient of the net force and mass of the object multiplied by the change in time. This formula is shown on line 57 using GlowScript. The position update formula, our second formula, is understood to be the final position equaling the initial position plus the product of the average velocity and the change in time. This is shown on line 59 in the GlowScript code. Moving on to the Tracker application, we can see the video used to find our experimental data. The video begins at frame 114 and goes to frame 144. This 30-frame window gives us plenty of data to use, as well as being a window where the baseball is close to constant velocity. The baseball had plenty of time to speed up to its constant velocity before entering the frame. The table and corresponding graph of our experimental data for these 30 frames is shown to the right of the video. From this data, we are able to derive our initial velocity in order to be used for our predicted data. Our initial position vector, which is only non-zero in the x direction as we are looking at an object that does not change direction, is 0.001867 meters. Our second position vector, or the position that we observed after 0.033 seconds, is 0.03637 meters. Using these two data points, we can find the initial velocity to be 1.0455 meters per second, as we took the difference of the x components of the two position vectors and divided them by the change in time, which in this case is 0.033 seconds. The initial velocity, as well as position and time, are shown inputted into our GlowScript code on screen. Now that we have found all the information we need in order to run a computer model to find the predicted results, we can use GlowScript to predict the motion of the baseball. For the code to run correctly, many inputs are needed. The mass of the baseball is estimated to be 0.145 kilograms. The position and time are both taken from Tracker, and the velocity was calculated moments ago. The net force must be zero in this case, as the velocity is meant to be constant, and the velocity is constant if and only if the net force is zero. When we run this program, one can clearly see that the motion of the ball follows a similar path to that of the baseball in the video, as well as the graph being very similar to the one in Tracker. Now that we have data from both Tracker and GlowScript, representing our observed and expected data respectively, we can graph the data using Excel. The line in orange shows the observed position versus time graph, while the line in blue shows the expected position versus time graph. The graph shows that the motion that was predicted was incredibly similar to that of the actual baseball rolling on the floor. The only slight deviations of the observed data below the expected as the time approaches 1 second are likely due to the force of friction, as we did not account for that in the computer model. It is impossible to simulate a frictionless environment in the real world as we did with the model, so the fact that the position was slightly below what we expected makes sense when looking at the context of friction. Also, friction is a force, which means that while we attempted to apply Newton's first law, we could not because the outside force of friction changed the velocity of the baseball. There are some final questions that we must answer before wrapping up the lab. The first is the simple idea of what if we were to flip the axes? How would our result change? Well, if this were to happen, the baseball would begin to travel in the negative x direction instead of the positive x direction, which would make our graph have a negative slope. And a graphical representation of what the data might look like in this hypothetical situation is shown on screen. Additionally, is it possible for us to say how many pushes and pulls are added together to give zero net force in our case? It is impossible in our situation to know the exact forces that were working on the object. Things such as friction and air resistance play a role, but we have no idea how much. What we can say is that the net force is zero if the velocity is constant, which, in the model, it was.